It's happening.
Excellent.
All right.
Great.
Thanks.
Thank you very much, Arne, for the invitation and the kind introduction. It's a fantastic pleasure to be here in front of you. So many eager to learn something about optical clocks and, of course, all the other quantum sensors that you will hear about this week. I'm from PTB, Physikalisch-Technische Bundesanstalt. It's Germany's National Metrology Institute. It's the oldest national metrology institute and indeed the second largest after NIST in the US. The tasks of PTB are determination of fundamental constants and, of course, dissemination of the SI unit system. And for that, and to realize the SI units ever more precisely. And for this, we develop new measurement techniques. And among those are, of course, also clocks. PTB has more than 2,000 employees and a lot of PhD students. We do a lot of research indicated by 600 publications per year or more. So this is the clock hall. It's a fairly old picture. The optical clocks are here in the background. They have grown. There's now, I don't know, 4 or 5 optical clocks in operation. You can see cesium beam clocks here, these two, and cesium fountain clocks in the back here, and then hydrogen masers here in the front. This is where the German time is made. However, it's not where the German time is distributed, because that's a transmitter. If you have a sort of a clock receiver, an automatic radio-controlled clock, then that signal is not distributed from Braunschweig, but rather from Mainflingen, which I think is not too far away from here, actually. So you should have best reception around this area. Okay, this is where I come from, and now I want to start by showing you a number. Yeah, I do not expect any one of you to know what that number actually is, but there's what's curious about that number. Yeah, what do you think is special about this number? Sorry? Indeed, it's a very long number, yeah, and the uncertainty given in parentheses here is at the 18th digit, actually. And I think it's fair to say that this is probably the most accurate measurement of mankind up to now, because it's the frequency ratio between an indium ion clock and an ytterbium ion clock, and it's the quantity that has been a non-zero and non-integer quantity with the most digits that has ever been performed. And the interesting part is that when we look at these optical clocks and their development, then there's, at least up to now, there's a lot of technical challenges that we have to overcome that I'm going to introduce some of to you. But there's no fundamental limitation inside, but there must be eventually in terms of relativity. Yeah. There's Planck time, and we don't know what's beyond that, but we are unfortunately very far away from probing that right now. Okay, 10 to the minus 18. That's a very, very small number. And it corresponds to this ratio, which is still a lot of digits, of course. Yeah, it's 300 times better than the best cesium fountain clocks. It means 1 second deviation in 30 billion years. So if the clock had been started, or that clock ratio measurement had been started at the Big Bang, the clock would go, or the clocks would go wrong by half a second by now. If you translate it to a first order Doppler shift, it corresponds to 300 picometers per second, or 30 millimeters per year, that you could measure in terms of the first order Doppler shift. Or translating it to a distance measurement, if you could measure the distance between the Earth and the Sun to 18 digits, that would mean that you could measure those 150 million kilometers down to 1,000th of a fraction of a human hair. I still have problem understanding it, yeah, what that actually means. It's just very, very accurate and precise. Now, One question I typically get when giving this type of talk is who the heck needs a clock with 18 digits? Yeah. And clocks have many applications, of course. There's actually currently there's two killer applications for these clocks. One is testing of fundamental physics because we can test theory predictions either in numbers or phenomenological. Here, this example is mostly phenomenological. We can probe for variation of fundamental constants because if, for example, the fine structure constant that controls the interaction between the electromagnetic interaction between electrons and protons, if that would change, then all levels in our atoms would actually change, and therefore also the clock transitions would change, and that would be different for each type of clock. And so if we do that type of ratio, we would see that ratio either drift or oscillate, and that could indicate that one of the fundamental constants is actually changing. We can perform tests of general and special relativity by performing redshift tests. Who knows what a redshift test is or where the redshift is what the redshift actually is? Anyone? What's the redshift in clocks? Have you heard? Who has heard about the redshift? Even if you don't know what it is, yeah? Okay. Somebody able to explain what it is? To recall? Yeah? Yeah. Yeah. That's one form of the redshift in astrophysics, yeah, that the further objects are away from us, the more redshifted their transition energies are, so that essentially all the optical spectra are in the deep UV, in the deep infrared or even in terahertz regime. Where you can now measure it, and we can even measure that on Earth, actually, this type of redshift, because it is a general relativistic effect that an object close or in a gravity potential ticks slower than an object away from it. So that means a clock on the floor here ticks slower than a clock on the desk, and the difference is the fractional frequency difference is 10 to the minus 16 per meter of height difference. And that means we can use clocks to measure height differences. That does not make sense if they're nearby, yeah, but if we connect clocks over a long optical fiber, and I'm going to show you how that is done, we can actually measure the height difference between these two clocks when we have clocks at the 10 to the minus 18 level down to 1 centimeter. Yeah, and there's no other technique capable of actually doing that. Clocks have been proposed for gravitational wave detection. They have been used to test local Lorentz invariance because that's maybe a little bit more intricate, but if you have different substates in your atom that you can populate, then the electron orbitals, they have, like, for example, p or f orbitals, they have a directionality associated with them. Yeah? So they're elongated in one particular direction. And that direction you can orient with respect to a possible ether in space, and you can measure one direction and an orthogonal direction, whether those frequencies are actually the same or whether they differ. And that's a test of local Lorentz invariance, preferred direction of space. Please. The frequency of the clock transition, yeah, where one starts typically from an S ground state, which is symmetrical, and then you either excite an orbital that is oriented in this direction, or you excite an orbital that is oriented in that direction, and then you compare the two. And if there's a frequency difference, that could be caused by a preferred direction in space. So far, I can assure you, yeah, nothing has been seen.
How does the gravitational field of the Earth actually look like? I mean, I think they have those measurements done with a satellite, right? Where they
Yeah, that's the next slide. Thank you.
and now if you go into this super near field in your laboratory, for example,
yeah,
Do you see those effects of things nearby as well?
No, we don't. Yeah, that's a very interesting point. The second killer application for clocks, besides fundamental physics, is this geodesy application, where you can measure geopotential differences, we call it. Yeah. And the geopotential of the Earth is shown here in this potato type plot from the Grace and Grace follow on satellite campaigns. There's two satellites that run after each other and accelerate or decelerate in the gravity potential of the Earth. And by monitoring the distance, you can derive plots like this, essentially. And what they can do is they can map out not only the gravity potential, but also higher order derivatives of the gravity potential, whereas clocks are purely sensitive to the gravity potential. Of course, we could go around the Earth and measure that, and then we would probably get a similar figure than this. But clocks are not particularly sensitive to the immediate surroundings because they're sensitive to the overall potential of the Earth generated by this gigantic volume of the Earth. And so what geodesists say is that clocks are typically sensitive to sort of regional gravity disturbances on the order of maybe 40 to 100 kilometers in the area. So if there's water or a cave of that order of magnitude, in the Earth, then we would see it with our clock. Atom interferometers are much more sensitive to local variations because they measure the gradient of the gravity potential. And by combining the two, you get two moments, essentially, of the gravity potential and can locate stuff that is changing or hidden underneath the Earth much more accurately. And then you can go on, of course, you can make an atom gradiometer that measures the gradient of the potential and so forth, and get more and more accurate.
So maybe you guys can also use the microphone when you ask questions. We can also circulate them. They don't have to stand there. It's just better for all my 400 YouTube followers that can also hear the question, you know?
I can try to repeat the question, but I'm not particularly good
at it.
But
I actually had a question. I mean, there is, what do we actually see there in the color code? Is it like the strength of the gravitational field?
Yes. Yeah.
And that's also the same, it's also mapped basically into the shape of
the height of the Earth, yeah. So it's mapped into the height. The process is much more complicated, yeah. And I'm not going to go into it. Yeah.
Okay.
Okay. Then there's other applications like synchronization of large networks. And I should mention that to actually do such tests, of course, you may want to have transportable optical clocks. And there's several European-wide programs to actually build and characterize transportable optical clocks, with which you then can go to other places and do that type of geodetic measurements. Similarly, for synchronization of large networks, you may be aware of these radio telescopes that are switched together, and their data is time tagged, that you can correlate it, phase correlate it actually, and then the entire Earth is essentially the aperture of this gigantic telescope that you can then make up. And you need very good clock synchronization to actually do that. And then last but not least, what you all have on your cell phones is a GPS or a GNSS, Global Navigational Satellite System receiver, with which you can pinpoint down your position very accurately. And it's also based on good clocks that are on board of the satellites. All right, that brings me to the menu of today. I want to introduce you to clocks, how they work, how they're characterized, how they're implemented, how you do frequency comparisons, how do you transmit the optical clock light over long distances, and what your clock species choices actually are. And then in the second part of the lecture, I will tell you about quantum enhanced clocks on the example of the aluminum quantum logic clock, because that's one of the clocks that we are building, and happens to be not ours, but the one at NIST, to be the most accurate clock in the world. I will then also talk to you about multi-ion clocks using dynamical decoupling. That's a technique also used in NV centers and quantum information processing, and we use it to make clocks better. And then last but not least, I will show you the first entanglement enhanced optical clock. All right, let's jump right into it. What is the principle of optical clocks? You need something that oscillates, a periodic event like the rotation of the Earth, a pendulum, or a crystal quartz oscillator. And when you then count all the cycles, you essentially build a clock. There's two slightly different notions here. One is a clock that then establishes a time scale, like our European time scale, or UTC, Universal Time Coordinate. There you need to count all the cycles without missing one, yeah, to establish a time scale. What we typically do with optical clocks is that we operate them as a frequency standard. And the advantage is that they can be interrupted. You can miss cycles and then just continue the measurement after the weekend, for example. But I will use the two terms interchangeably, but you should be aware of this distinction. Now, once you have a clock, of course, you want to know how good it actually is. And there's two main notions, which we call stability and accuracy. Or rather, what I prefer more is the statistical uncertainty of the clock and the systematic uncertainty. So what are these two? You can see here in this plot a time trace of a frequency measurement, for example, a clock ratio measurement. And the red line here indicates the unperturbed transition frequency of your atom, for example. And then you see that there's a data trace which has an offset. The mean value has clearly an offset and a lot of scatter. And the offset means that we have a systematic uncertainty because we do not reproduce the unperturbed transition frequency, and the scatter indicates that it's fairly noisy, that the statistical uncertainty or stability is not very good in this clock. In the next example here, the statistical uncertainty is much better because the noise is less, but the offset is still the same. And by the way, it's like throwing darts at the target. If you are reproducible, or if you always hit away from the center, but with low spread or low scatter, then you're very stable, or your statistical uncertainty is very small. We can have all the two other cases as well. We can have a lot of scatter and be on the unperturbed transition frequency, or, and that's what we like most, we hit the center here of the dart target and with very low scatter. And that's a clock with very high stability and very high accuracy. And these are uncertainties of type A and type B that you may have come across in your studies already. Now, one of the big problems in clock measurements is that we cannot calculate the unperturbed transition frequency in our atom. We just measure something, and then we have to deduce all possible frequency shifting effects from the unperturbed transition frequency, and that's the really hard part in the clock business. All right, now what's a good clock? It's obvious that mechanical devices like crystal quartz or pendula are not very good because they depend strongly on the environment. We need a stable unperturbed reference. Yes? Microphone?
Oh, can you please go back one slide? Okay, so I like kind of don't understand that the for the inaccuracy, what is like unperturbed reference reproduced how well? So I don't understand this thing.
What the unperturbed transition frequency is?
Unperturbed reference that you if you reproduce it well, then you call it more accurate. And
Yes.
how this line incorporate with this graph?
Ah, okay. So the red line here is the hypothetical. If we could calculate the transition frequency, then that line would represent the transition frequency. Let's assume we can calculate it, yeah? But what our clock output is actually this data, which has an offset from the unperturbed transition frequency. And I'll come to this in a bit more detail, yeah? What could be the cause of this offset? For example, magnetic and electric fields that shift your transition energy because they are present in the magnetic field of the Earth or other from other sources.
So like the red line is like you theoretically calculate.
If we could, that would be the red line, yeah? And the problem is that we don't know where the red line is. That's a difficulty. Okay, so what's a good clock? Obviously, mechanical, man-made or women-made pieces are not. But atoms are ideal, as we now know. And that has been discovered actually or mentioned a long time ago by James Clerk Maxwell, who already said that if we want to obtain standards of length, time, and mass, we should seek it in the wavelength, the period of vibration, and absolute mass of molecules and atoms, of course, as well. And so the idea is very old, and it has now been implemented with a new definition of the SI system. Now, in terms of clocks, the first clocks had been implemented, or the first atomic clock had been implemented by Essen and Perry and PL in the UK in the 50s. And ever since then, they made a lot of progress in terms of the systematic uncertainty that they get. They're now at a few 10 to the minus 16 systematic uncertainty in their relative frequency ratio, or the relative frequency uncertainty. And we call that the Moore's law of optical of clocks. Now, if you look at this, it's leveling off here. Yeah, there's no cesium fountain clock that is below 10 to the minus 16 because they have like 20 systematic effects they have to account for. They all need to be improved at the same time to make the clock better, and that's very tedious. In particular, because it takes a fountain clock weeks to average down to 10 to the minus 16. Now, in contrast, optical clocks had been started, or people have started working on optical reference transitions in the 80s. And then, of course, there was laser cooling invented and many other techniques. And so the progress in optical frequency metrology was quite dramatic and fast, overwhelming now the best cesium clocks by a factor of 100 or so in statistical and systematic uncertainty. If you look at the latest, maybe 5 to 10 years or so, you might see that there's a leveling off here as well at 10 to the minus 18. Yeah, and I show you some examples why that's just very hard to overcome and just to continue on this line. But the cesium clocks has worked so well that since 1967, the unit of time, the second, is defined on the cesium hyperfine transition in the ground state. Which means, so what do you think is then the problem with all these frequencies that lie below the cesium frequencies?
Maybe that we have no reference to check whether it's actually accurate? Whether we really reach that?
We can no longer use cesium as a reference because we cannot realize cesium with more than 16 digits and compare it to some device that has 18 digits. And in fact, it means that we cannot provide, or we can, yeah, but only with limited resolution, the transition frequency of all of these standards in hertz, because the unit hertz is only accurate to 10 to the minus 16. So what we have to do is measure frequency ratios like the one that I showed you at the beginning of the lecture. And here are a number of, these are not all clocks that there are in the world, but some of the most accurate ones, like the aluminum clock, lutetium clock, strontium lattice clocks, ytterbium lattice clocks, and ytterbium single ion clocks.
Sorry, but can't you just measure the number of oscillations of the cesium fountain clock with an optical clock?
But the unit that I attach, the hertz, is the problem.
But it's just a number. There's no uncertainty in the number.
No, but the unit hertz needs to be realized, and it's realized by counting X number of cycles in the cesium transition, and that counting has an error, which is given by 10 to the an uncertainty of 10 to the minus 16. So there's no way around this, yeah, because I cannot count the cesium transition frequency better. It's when you do if you have a meter stick, yeah, that's wrong by a millimeter, likely, yeah, then you cannot do a measurement that's more accurate than a millimeter. Yeah.
What is stopping us from defining a new standard?
That's a very good question. Yeah. We're working on it. Yeah. There's a committee who has set out a roadmap for the redefinition of the SI second. There's a number of primary and secondary criteria to be fulfilled. And one of the least fulfilled criteria is frequency ratio measurements, reproducible frequency ratio measurements between different laboratories that would coincide. Yeah, and I will show you an example where this is a problem. And we're working on it. Yeah, but then who's going to decide which of the many species we pick? Yeah, is it going to be one species? Do we average over on a sample of transition frequencies? These are very and highly political questions, unfortunately. So I think it's going to take the next chance for the redefinition would be theoretically 2030, which I do not believe in. I think it's going to be at the earliest in 2034 that the SI second will be redefined. Okay, now how do optical clocks work? First of all, we need this oscillator that I was mentioning. And this is now, it's slightly different from what I showed you in the beginning. We have an oscillation, and this oscillation is our laser in this case. But a laser is a technical device. It drifts. Yeah, it's not stable. So we need to stabilize its oscillation frequency, its color, to an atomic reference. And so we use the laser to probe a transition, and then we can do internal state detection and provide a frequency feedback. Typically, in the simplest case, we can model this as a three-level system where we have a ground state and an excited state, a metastable excited state that is long-lived, typically to provide a narrow transition, a narrow resonance in this case on this transition here. And then we can use a second transition to a third level up here. That's a cycling transition, lasered cooling transition typically, where we scatter millions of photons per second. And so if we, after applying the clock laser here, remained in the ground state, then the ion or the atom is bright because we scatter millions of photons here. If you were able to bring it into the excited state, it gets dark. Yeah, and this is the only information that we ever get from the system. Yeah, either it's bright or it's dark. But by doing clever schemes, and I'm going to show you how this works in a minute, we can then derive the frequency deviation of the laser from the atomic transition frequency and feed back to correct for any offset like this. But this does not yet mean that this is actually the unperturbed transition frequency. Yeah, that's a different story. Yeah? That's a transition frequency realized in our experimental setup. Okay, and then once we have stabilized the laser oscillator, then of course we need to bring it into applications, compare it to other optical clocks, for example, or measure the cycles to establish a time scale. And for this, we need an optical frequency comb. Do you know why we need an optical frequency comb? How can we count optical cycles? Or why is it difficult to count optical cycles? Bear that in mind. Oh, yeah, okay. Maybe you know.
Yeah, I guess because the cycles are so fast that you don't have electronics to keep up with it.
Indeed, yeah. It's at hundreds of terahertz. No electronics can count these fast cycles. Yeah, you can count up to maybe hundreds of gigahertz or so, but not terahertz. And so we need a divider to divide it actually down into the countable regime. And that's exactly what a frequency comb does. Okay, so just an analogy how optical clocks work. It's like tuning a musical instrument. You have your violin, and you have your reference measurement apparatus here that tells you whether the violin is tuned too high or too low. And by changing the tension in the string, you can change the pitch. And that's a frequency feedback that you manually typically apply until you're right on the center. And that's exactly how an optical clock works. Now, any idea why we cannot use just the, I mean, there's an clearly there's an oscillation in the atom as well. Yeah, why can we not use that? Why do we have to use a laser to actually excite the atom and then indirectly infer the transition frequency? Why can we not measure the oscillation in the atom directly? Yeah.
So like maybe we have to get some information from the system, and like for the atomic transitions we are not always sure about the transition. So maybe for that we use a laser to like stimulate the oscillation in the atoms, and then we use the feedback to get the information of the oscillation.
Yeah, so I think you're getting the point correct. Let me try to rephrase your comment. So in principle, to excite an oscillation also with a crystal quartz or with a mechanical clock, you need to put energy into the system first to start the oscillation. And we could, of course, put the atom into an excited state, yeah, and then watch it decay. That decay is so terribly slow that we cannot get enough signal-to-noise ratio from the emitted photon that we then would measure essentially. That this is not a very practical scheme. And so we need to put in energy by the laser, yeah, and by doing sort of doing coherent manipulations of the internal state, we can get a handle on the phase evolution, differential phase evolution between the atom and the laser, and then read that out using the atom with near 100% fidelity, actually. Yeah? So that's a much more efficient way of getting that information. Yes?
I have two questions. So the first would be, what is an optical frequency comb? And the other would be, when you say you can't measure the transition frequency directly, what do you mean with directly?
Without using a laser.
Like how would you do that?
Or essentially looking at the atom oscillate. That's what I mean. In principle, you could watch the photons decaying from the atom, and their energy would resemble the energy difference. That's what I would call a direct measurement, a fluorescence measurement, essentially. Maybe you're familiar with that.
So you would excite it using something other than a laser?
I guess you could use a flash lamp. Yeah, it's not particularly efficient, but you need to put energy in to bring it into the excited state.
And what you're doing instead is you're driving a cycling transition.
That's a detection technique that we're using instead. But what I mean by directly or indirectly is a fluorescence measurement versus a Ramsey or a Rabi frequency measurement that I'm going to show you in a minute. Also, the frequency comb is part of the lecture. Yeah, I'm going to show you that in more detail. All right, so let's briefly show you how Rabi spectroscopy works. Who does not know what Rabi spectroscopy is? Sure. Okay, there's a couple. So it's worthwhile going through it step by step. So what we do is we prepare the atom in the ground state. That's where it naturally resides anyway. And then we apply a spectroscopy pulse with our laser. And that, in general, brings the atom into a superposition of, and I call that the spin down state and the spin up state. So we can, in this very simplified model, we can model the atom as a spin 1/2 system that has two projection states. Yeah, one is the spin down state and the other one is the spin up state. And then, of course, we can have complex combinations that are given by these coefficients here. And in an ideal case, alpha and beta would be 1/square root of 2. That would correspond to an equal superposition of both internal states. Now, that's the superposition in terms of populations. And then when I apply now a laser on the cycling transition, then the system needs to decide. Some people call that the collapse of the wave function. It's not a term that many people like. Yeah, it's just a statistical measurement in which what the probability actually is of finding the atom in the spin down or the spin up state. And the probabilities are given by the square of these two amplitudes. Yeah, but whenever I do a measurement, I only get it either bright or dark after the measurement. Yeah. And so that's a single bit of information I get. Yeah, that's not a lot. Yeah, and so from a single measurement, I do not know the coefficients alpha and beta that I would need to know. Yeah, to be able to tell where I'm on this resonance curve. Yeah, so this is a resonance curve as a function of the detuning, and this is the excitation probability. Essentially, this beta squared here. And so to get this type of curve, I need to repeat that measurement tens of hundreds of times, actually. When I'm at the resonance, most of the times I get it to be dark, yeah, in the spin up state. And when I'm very far detuned, then I haven't managed to bring it up here. And most of the time I get a bright ion corresponding to the spin down state.
Sorry, can you just go into a bit more detail about the measurement process? I mean, so what the laser parameters are, for example, and what you're changing as a function?
I will come to that.
Okay.
Yeah.
So you mentioned that we can repeat with the single atom many times as well. We can use many atoms at a single time. But when we use many atoms at a single time, how do you define the reference? Because if we don't know the exact number of atoms, many atoms, we don't know so we only get the bright or dark. So in our data, we can only get the data of the bright, but we have to know the bright plus dark.
Absolutely.
Yeah.
And people do that type of measurement for exactly those reasons. Yeah. So they measure both parts of the, they bring the excited state back down and measure again, for example. And then you know both parts of the wave function or the overall number of atoms.
Don't understand like how to.
So first a measurement is done in this configuration here. Yeah. So then you know essentially the alpha squared with modulo a normalization constant based on the number of atoms that you have. And then you bring down the spin up states down to this level, back down, and you detect again. And then the sum of both detection events gives you the overall number of atoms and then the ratio,
okay.
The individual components. Okay. And so what we then do is we change the spectroscopy laser frequency as you can see here. So
sorry, I have a question here.
Yeah.
So here you put the spins, right, as states, but in previous slide you use 500 terahertz to excite your system.
I used what?
500 terahertz. 500 terahertz.
Yeah.
And 500 terahertz is around 600 nanometers, right?
Yes.
And it corresponds to the electrical transitions.
It is, yeah.
But here you put spins.
I still call it a spin 1/2 systems, despite the fact that it's actually an optical transition to a different orbital in the atom. Yeah, but I can model it as a spin 1/2 system if it's just two internal states. I'm not actually flipping a nuclear spin or an electron spin. I really excite it to a new orbital, but the physics is identical in the end. Yeah, that's a very good question. So what I can do now is I can change my laser frequency, scan over the line, and then try to determine the line center, and how that goes in detail. I show you in 2 slides, I think. Yeah. Now, what you see here is already that we have a full width, a certain line width. In this case, I think it's 2.7 Hertz, full width half maximum, and it's clear that the narrower this line width is here, the easier it is for me to determine the line center with very many digits. Yes.
Thanks. I wanted to ask, you said that you excite the atom to the excited state. Do you create a coherence between those 2 states, or you bring to the...
Oh, it's a coherent superposition.
Exactly. Okay.
Yeah. Like shown here, this is a coherent superposition. Now, what determines the line width of this transition that I've shown here? Where's the line width coming from? Yeah.
The lifetime of the state?
That is one limitation. Yeah. It's not the limitation in this case, actually. What else?
The laser line width?
Yeah. It's also not the laser line width in this case. That's a very good point. Yeah. But the laser line width has something to do with it.
Maybe temperature of the
No.
of the
It's not the temperature. Yeah. You have to speak into the microphone, please.
Yeah, I think it's because the uncertainty principle. Because when the
Yes.
yeah, when your lifetime is, I mean, it's very narrow, so the line width could be broadened.
Yes, and I'm interpreting what you said. By lifetime, you mean the length of the sequence, which is in this case the length of my Rabi spectroscopy pulse. That's exactly right. Yeah. So the lifetime could be limited either by spontaneous decay, yeah, the excited state lifetime of the atom that gives you a finite line width, or how long I choose to probe, yeah. And if you could also call that saturation broadening, yeah, because I have to apply a lot more power to my atom to excite it faster than the excited state decay time is, and then you power broaden it to that line width, and that's given by the uncertainty relation, essentially. Delta E times delta T is h bar divided by 2 or so, yeah.
Out of curiosity, what's the laser line width?
So typically, and that's why this was a very good point, yeah, you choose your probe time as long as possible. And the limitation in our days for many of the high-performance clock systems is actually the laser coherence time, the line width of the laser. That dictates how long you can probe.
So it's also 2.7 Hertz.
No, it's probably narrower, but you want to stay away from that line width by a sufficiently large margin. Okay, so that's Rabi spectroscopy, and now let's go to a different technique, which is called Ramsey spectroscopy. It's very similar, but maybe a bit more elegant, yeah, and it gives you a larger signal-to-noise ratio. So I'm sorry, this is pedagogically not favorable, but I'm now starting in the excited state because I did not have time to redo my Bloch vector simulations to start with a spin down state. Yeah. So let's assume we prepare the atom in the spin up state here, and then what we can do is we can apply what we call a pi/2 pulse. This is nothing like, this is exactly identical to a Rabi spectroscopy pulse, it's just shorter. And what we do is we do not detect afterwards, yeah, but we apply this short pulse, generate a superposition here with amplitudes that I did not write down, but it's typically an equal superposition of ground and excited state. And then we wait. And during this wait time, we get a phase evolution according to the energy difference between the two states. And that's shown here, and I'm going to repeat that one more time. It's the so-called free precession time, T or TR, where we acquire a differential phase evolution between the two spin states here in this case. And that difference in the frequency is given by the frequency difference between the atomic transition frequency and the laser frequency. And that you can depict very nicely on the so-called Bloch sphere that I'm showing down here. And now I have to repeat that animation here. So this corresponds, okay, maybe I should explain what the Bloch sphere is first. So if this red arrow is pointing upwards, it indicates that we're in the spin up state. If it's pointing downwards, it indicates that we're in the spin down state. If we have equal superpositions between spin up and spin down, we are on the equator here, where we can have, for example, spin up plus spin down in this direction, spin up minus spin down in this direction, and then spin up minus I spin down in this direction, and spin up plus I spin down in this direction. Yeah? So we can visualize all possible combinations of spin up and spin down in the complex plane on this equator here, or on the Bloch sphere, and then equal superpositions are on the Bloch sphere. And what we do in the Ramsey experiment, we bring it onto the equator here. And if you're on resonance, then in the rotating frame with the laser frequency, nothing happens. And the second pi/2 pulse that we apply at the end of this free precession time then simply continues and completes the first pi/2 pulse to a complete pi pulse and brings it to the spin down state. Whereas if we had some phase evolution, and now I'm going to repeat it again, here, and we apply the second pi/2 pulse, then the angles no longer match, and we do not end up in the spin down state, but in a slightly different position here. And that deviation, or the change in the excitation probability directly relates then to this detuning here between the phase evolution of the atom and of the laser. And a spectrum from a cesium fountain actually looks like this. It looks very similar for atomic systems as well, but this features a very high signal-to-noise ratio, so it looks very beautiful. And if you zoom in right into the center, you can see the central fringe, which also looks, I mean, it's not a Rabi excitation because it's a sinusoidal signal here, but it provides you a center frequency and then a slope where you can measure any deviation from your phase evolution by a change in excitation probability that you get on the slope in the end. And again, the longer the Ramsey times TR is, the longer the wait time here, the more phase difference you accumulate and the narrower the fringes here become. And one special feature of Ramsey interrogation is that the observed line width is 40% narrower than the comparable Rabi line width for the same duration of the experimental sequence. And that's, of course, an advantage because it gives you a higher signal-to-noise ratio. Okay, now, yes?
Shape the baseline takes such a... So I wanted to know what's the reason behind why the baseline takes such a shape? Let's suppose we go to the right of 0, we see it going up and then coming down.
You mean this slope here?
Yes.
That is a consequence of the Rabi, the Ramsey pi/2 pulse widths. So the shorter these pulses are, the broader the spectrum becomes. And that's just some interference pattern from the pulse shape, the rectangular pulse shapes that we apply to the system.
And the reason behind the decay is dephasing. Is that correct?
It's just the spectral bandwidth that you can address in these pulses. So you run out of, if the detuning becomes too long, then now I need to think where this is coming from in the end. I'm not sure if it's dephasing. I think it's if you're detuned with your laser too far and the pulse is not short enough, then you cannot actually excite it. You do not bring it all the way to the equator any longer. Yeah, because for this to work as a pi/2 pulse, yeah, you need to be on resonance, and the further you are away from resonance, and that's this detuning here. The less efficient a pi pulse it becomes, and then it stops working as a pi pulse, and then the shape breaks up, essentially. That's the reason behind it. So it's not a dephasing, it's a fully coherent evolution as expected. So you can calculate this line shape by implementing these pi/2 weight and pi/2 pulses with a certain detuning, you get exactly this shape.
What is the readout strategy difference between Rabi and Ramsey?
It's identical. So also at the end of the Ramsey spectroscopy sequence, we just apply our cycling transition laser. That's the yellow one here. So we just simply apply this laser and then detect the population in one of the two states, essentially. And then, well, either we know it's just one atom, or we know it's several atoms, and we need to measure both populations to get the total number of atoms in the system.
Is it the contrast difference that defines the line width or something else?
The contrast difference between what?
Is it, I mean, when you're reading it out, what are you reading out exactly? Is it the image contrast difference or?
No, we do assume that we have essentially 100% detection efficiency in our systems. So we can distinguish dark from bright with extremely high fidelity. So the readout error is typically in all the systems, atomic systems that I'm talking about, quantum projection noise limited. And we come to that, yeah, what that means actually.
Sorry. I had a question in the Rabi spectroscopy. So why does the transition probability peak doesn't occur exactly at 0 here?
Oh, that's because we drew the scale.
Okay.
Like this, yeah.
And also, can you tell me about that 300 millisecond probe time? What does that mean exactly?
That means that the Rabi pulse was 300 milliseconds long.
Okay.
With which we tried to generate that superposition. And of course, we have to dial in the correct laser power to power broaden the transition, that the 300 millisecond pulse on resonance gives you maximum excitation probability. Any more questions? I like this, yeah? This is really nicely interactive. Okay. So now we have line shapes that provide us with a slope and a center. So we have a center right here, and we have slopes on the side that indicate to us when we're off the center. And now I'm going to show you how we implement that feedback loop, just at the example of the Rabi line shape, but it works for Ramsey just as well. So what we do, we call that two-point sampling. We probe our atomic transition at a specified step red and blue detuned. Red detuned means lower frequency, blue detuned means a higher frequency, and that step is indicated by delta M here. And we suppose we know the transition frequency, where that is and how large the step is that we would need to make to get to half the excitation point here at 0.5 roughly. And so we apply that step, measure the probability of excitation, go to the other side, measure again the probability, and then most likely we will end up in a situation like this, where there's an imbalance because we did not, in fact, start at f0, but our laser has drifted in the meantime, and we start at a different frequency value, much more here in this area. And how we can do that, I've mentioned that delta M is chosen that under ideal conditions we do half excitation here on the 0.5 scale here. And then what we can do is we can derive an error signal. That's the difference in excitation probability that we measure here on this point and on this point multiplied by the step that we have actually taken. And we can then add this correction to the laser frequency by using an acousto-optical modulator. For example, we tune the frequency of an acousto-optical modulator and then steer the laser's frequency back towards the transition frequency here. And we do that typically in a proportional and then integral and double integrator system. And I think it's one of the problems that I've written down, for you to find out why we need a double integrator. And so doing this type of feedback loop, and we do that repeatedly, we steer the laser's frequency onto the atomic resonance frequency. And now that brings you to the full clock sequence. How does that look like? We start typically with laser cooling of the atom, and that's an ion clock in this specific case that takes maybe a couple of milliseconds or so. We then do a state preparation that takes on the order of a millisecond maybe to pump it into one of the clock states, because we never have just 2 or 3 level systems. Usually we do have a Siemens substructure that we have to take care of and prepare into a specific state. Then we do the clock interrogation for hundreds of milliseconds, and then we detect afterwards whether we made the transition into the excited state or not, and that's typically on the order of 10 milliseconds. And then we repeat, we start all over. And if we do that as a function of frequency detuning, we get such a Rabi line shape. But since we do not get a lot of information here in the wings, we always, once we scanned across and know roughly the center frequency, we always do this 2-point sampling where we get the maximum information out of our atomic system and steer the laser frequency. All right, now we know how such a clock system works. And we can now compile a wish list for small statistical uncertainty.
Sorry, can you go back one slide? So after that, you have basically amount of photons collected for the settings here currently.
Yes.
That's not a full cycle, right? Because you need to do 2.
Yeah.
So it's basically repeating that again with, let's say, the minus frequency.
I know we do plus and minus typically at the same shot. I mean, it gets a bit more complicated, depending on the system and what you do. You can leave out state preparation between probing F plus and F minus. That's what we typically do. So we have to start with laser cooling again, then do the clock interrogation and then the state detection. And typically in our clocks, we do that 5 times for the plus and the minus transition or slope here. And then we go to another Siemens state, namely this Siemens state here, and then we do that again, the same cycle.
But ultimately, you have a number of photons collected.
Yes.
Plus the set laser frequency of your laser. Those are the 2 or the voltage to the acousto-optical modulator, if you want. Okay, cool. Thanks.
Sure. Yeah. Microphone, please.
Is there a particular reason why we are choosing a spin 1.5 system versus a spin 1?
No, it's never a spin 1.5 system, actually. Yeah, it's just the way we model the system. If we have two if we have two states, one ground state and one excited state, then the proper description is a spin 1.5 system. In reality, it's a multi-level system that would require a lot more complicated description beyond the spin 1.5 system, but we can neglect that for most of the atom laser interaction here and do it step by step such that we address only a spin 1.5 system during clock operation. Okay, now what do you think? What do we need to get the best statistical uncertainty? Yeah. Microphone.
Back one slide, please. Sorry. The probability does not reach 1. You said you completely polarize your...
Yeah, that's experimental imperfections.
Okay, so there is, if during measurement you have other states coupling in or contributing to population.
Yeah, it's typically imperfect state preparation, or, I mean, this is a quantum logic clock, so there's a lot more behind this that I did not show you, but will show you in the next lecture. And those pulses can all be imperfect. And that's the reason why we don't need to reach 100%. Yeah. So what's on your wish list? If you wanted to make a clock with the lowest instability with...
have a state with infinite lifetime?
Yes. So a very long lifetime.
And have a readout which has infinite narrow line width.
Check, we have that. Yeah.
And
infinite lifetime. Yeah, okay. Yeah. Nominally, that's correct. Yeah.
And no decoherence of the system.
That's always a good idea.
That's also the lifetime, yeah.
Absolutely, yeah. So the best laser in the world, essentially.
Yeah.
Looking at this, so you want to minimize this ratio, essentially, yeah. So what else can you tweak on? You can make F0, of course, yeah, very large. That's the reason why we go optical. And then you also can probe more than one atom. You can probe multiple atoms to increase your signal-to-noise ratio. So essentially, we want a high transition frequency. That was the main motivation to go to optical clocks, because then you can measure time more accurately if you have more oscillations per time. We want long Ramsey times, which, as we argued, we can do if the lifetime is long enough and the laser coherence time is long enough. And we want a large number of atoms. And because, so this is me drawing quantum projection noise, yeah, for a single atom. And if you have multiple atoms in a single shot, you do multiple experiments at the same time and get your transition probability with less noise. And that's exactly what you want. And so in the end, all is combined in the formula for quantum projection noise, which is given here. And the first exercise for tomorrow afternoon will be to derive that formula for a Ramsey experiment. And you have all the ingredients on the slides. Not all of them, but almost all of them. Yeah. Okay. Now, this is where we're at. So this formula fundamentally provides you with the expected instability of your clock or the statistical uncertainty. And we typically plot that in the form of an Allen deviation. That's also part of the problems, yeah, to familiarize yourself with Allen deviations. For this plot, it's sufficient to say that we plot the statistical uncertainty as a function of the interrogation or averaging time. And of course, the more experiments I do, the more data I accumulate, the better the statistical uncertainty should become in an ideal world. And this is what I've depicted here. So this is a statistical uncertainty, or a typical statistical uncertainty for a single ion clock. And this is the statistical uncertainty for a lattice clock. I have not talked about the different types of clocks. I will mention that towards the end. Just a brief comment, yeah. So a single ion clock, as the name says, yeah, we just trap one ion and we probe just one ion all the time, yeah, and do the cycle that I'm describing. In an optical lattice clock, we trap hundreds to thousands of atoms in an optical lattice and probe them simultaneously. And now you already know, yeah, why the statistical uncertainty of lattice clocks is better, because I have a larger n. Yeah, n is not one, but 1,000 maybe. And one of the problems with single ion clocks, and I think it's probably the problem of single ion clocks, is that with a stability like this, or even slightly better, you would need 12 days of 24/7 averaging to actually reach 10 to the minus 18 statistical resolution. Yeah, so it goes on here. A day has 86,400 seconds, and you need 12 of those days to actually average down to 10 to the minus 18. That's a bummer, yeah, especially for PhD students who need to keep the clock operating for this long amount of time, and that's not easy. And now the interesting point is, if you plug into this quantum projection noise formula here, the maximum Ramsey time that you could afford, given the excited state lifetime of, for example, aluminum, you would actually end up here. Yeah, aluminum has an excited state lifetime of 20 seconds. If your Ramsey dark time would be 20 seconds, then your statistical uncertainty would be here. And you could reach 10 to the minus 18 in a day or less. Yeah, that's a huge benefit, obviously. And the question is, why do we not reach that? Why don't we just probe for 20 seconds? Yeah. Any ideas? I mentioned it already. No pressure.
Oh, no.
It's the laser. Yeah, the laser coherence time is simply not long enough for us to probe for 20 seconds. And this is why we need to develop better lasers. That brings me to the laser. So how do typical clock lasers look like? We have a laser out of the box, and that typically has a terrible stability in terms of frequency noise. And so what people typically do is they stabilize it to passively optical cavities, passive optical cavities that are passively stable, reference cavities, and because the cavities have resonances every lambda over 2, yeah, where it's a standing wave inside the cavity, and every time another lambda over 2 fits into the cavity, there's a new resonance. So in frequency range, the resonance spectrum of such a cavity looks like this. We have a spacing between these resonances given by the speed of light divided by 2L, where L is the length of the cavity. It's 2L because you need a full round trip. You need to account for a full round trip. And therefore, the position of these resonances here are directly related to the length of the cavity. So if the cavity length changes, all these resonance frequencies change, of course. And if you start counting from 0 all the way to the optical, there's a very large number multiplication factor. So the tiniest change here leads to a huge change in frequency here. That means that we need to keep the cavity length super stable. How stable exactly? Yeah, for 10 to the minus 16 instability, relative length change smaller than 1/100th of the radius of a proton is required. That this is actually feasible, I find mind-boggling, but it actually is, yeah, because you average over a very large area with your optical beam, and therefore can determine the distance between the mirrors of your cavity to better than 1/100th of the proton radius. So if you look at typical line widths of these cavities, given the mirror qualities that you can achieve, then this is typically kilohertz, and we would like to have clock laser line widths of 100 millihertz in the end, or better. Now the limitations.
Sorry, can I actually just find it mind-boggling for a second? It's just what's the thermal motion of the mirror atoms compared to that? I mean, they must be moving around individually, right? I mean, there's nothing is stable towards like hundreds of a proton.
That's our enemy, thermal noise. Yeah, it's Brownian motion of the cavity spacer, the mirror substrate, and the coating. And the last enemy now is the mirror coating, actually. Yeah, that this is still, it's typically amorphous coatings, and they have a very large motion given a certain temperature.
Yeah, but I mean, like, do you know how much it is in
Oh, it's the limitation.
in proton radius? I mean,
Yeah, it's pretty much this value. Yeah,
like proton radius over 100.
yes.
I see.
Yeah.
But that's also ridiculously small.
Yeah. Well, it averages
But
out. Yeah.
Yeah, but that's the thing. Like it averages just because you
You're probing
illuminate.
many of them. Yeah. 10 to the 23 or so.
Exactly.
roughly.
And then you find the average of those.
Yes.
And that's not moving. Individually, they are moving.
I have no idea how large the individual movement is. I cannot tell you. Yeah. I'm sure some solid state physicists can tell you.
Probably.
Yeah. You had a question? Okay. Now, what are the challenges, the technological challenges we have to face? It's electronic noise, because we have to resolve the cavity line width by 10 to the 6. Yeah, that's not easy. We have intensity noise on our laser. There's absorption in the coatings of our mirrors. Intensity noise means that the absorption changes, that changes the heat load that is absorbed by the coatings, and therefore their temperature. That leads to a change that can be up to 100 hertz per microwatts, which means that you would need, since we put in only a couple of microwatts of laser power, that we're close to the shot noise limit of the detection of the light intensity that we need to stabilize. So we're at the edge, essentially everywhere in this system. Yeah, as Arne also very well knows, of course. Yeah. Thermal expansion is an issue. Vibrations are issues. Yeah, so these are just typical numbers that have been achieved. And then our main enemy that luckily we share with gravitational wave detectors, and we're working on in our cluster of excellence quantum frontiers together with the gravitational wave detector people, is thermal noise. Yeah, as we discussed. Yeah, the Brownian noise of the spacer mirror substrates and coatings. That is a huge problem. And just to give you, I have the time to go into much detail on this, but one way to go to mitigate that thermal noise, and that's an interesting part, that the fact that the thermal noise was actually limiting all cavities up to then was only discovered in 2004. That's 21 years ago. Yeah. Up until then, people thought they just need to get higher finesse mirrors, improve their electronics, and just get better. But nobody did, despite trying really hard. And then they discovered a thermal noise issue, that this was the actual limitation. It was dead on the best cavities that were available at the time. And since that was
thermal noise at what temperature?
Room temperature.
Okay, well, cool it.
Yeah, but why would you cool it? Yeah, if you don't know that you're limited by the thermal noise. Yeah. And only after that has been discovered and the physical mechanism behind it was discovered, people could engineer their cavities such that the performance got better. And the first step to do was use materials with a higher mechanical Q factor. I don't want to go into the details, but the higher the mechanical Q, the lower the thermal noise. And it has to do with the fluctuation dissipation theorem. Yeah, read it if you're interested in it. So people went from glass materials as the spacer material to single crystals. For example, silicon single crystal materials, where luckily you have a transparency window at 1.5 microns, so you can make the mirror material, also the mirror substrate, also from silicon single crystal, and optically bonded onto this football-shaped cavity. Now you still have the thermal expansion problem. Silicon has a zero crossing in the thermal expansion coefficient at 124 Kelvin, so you have to cool it. This is why you have many shields, and there's essentially nitrogen cooling inside the system. And that has evolved over the years, and this is still the current best 2 laser cavities in the world, flooring off at I think 8 times or 6 times 10 to the minus 17 in once over this integration range here, giving a line width of 8 millihertz in a bit node. Yeah, it's mind-boggling, unbelievable. Yeah, that this actually works. The remaining problem here was that they used amorphous coating still on their mirrors, which is not a single crystal, has very low Q, and dominated, was responsible. That's the green line here, essentially. That's given by the coating. Now, the next idea is, why don't we use single crystal coatings? And so they did. Aluminum, indium, gallium, no, aluminum, or indium InGaAs coatings. I don't remember the composition, yeah, but it was grown by atomic layer deposition, single crystals essentially, and they could demonstrate a tenfold reduction of Brownian noise in these high reflective optical coatings. Now, the latest news on that is, I'm not sure if this is on, no, it's not on here, is that they've discovered now a new noise source in these single crystal coatings that up until that has been discovered 2 years ago, yeah, nobody has a clue, yeah. It's now the limitation at pretty much the same level. It's so-called birefringent noise, yeah. It has a component that is apparently common to both polarization directions, that you can put on these cavities. And if you average both polarization components, then you also average part of this birefringent noise. But then there's a global noise component still left over that nobody has a clue where it's coming from. Yeah. So please get to work. Solve it.
Would it make sense to go to even lower temperature? I mean, I know
that's what people now do, yeah. But apparently, if I remember correctly, that noise is still present at lower temperatures even.
But I mean, you also cannot go to low temperatures because you will always put some heat in from the lasers.
But that still works, yeah. I mean, you can
like millikelvin, I mean.
Yeah, but I think that's not necessary. Yeah, if you go to liquid helium 4 Kelvin, that should be sufficiently to freeze out the thermal noise, and that's what actually people do now. They go back to amorphous coatings, but go to colder temperatures. Yeah. Okay, and then there's of course for transportable clocks, you also need transportable cavities. And those can also be built through excellent engineering and ingenious ideas. And that's done by Uwe Ster and colleagues at PTB. So he's the master of our cavity.
Yeah, I also want to, I know Uwe Ster for quite some time. I built also some cavities in my PhD diploma thesis in 2006. And I remember Uwe Ster already at that time running around looking at cavities and really being an expert in the field, also working at PTB. So
yeah. So if you're interested in cavities, ask him. Yeah, not me. Okay, future trends. I'm going to skip for time because I'm going to go into more details about this in the next lecture. Let's move on to frequency comparisons. How to count optical frequencies, we've already discussed that you cannot electronically count them because they're super fast. Yeah. And in former times, people have gone to the lengths of building up divider chains chains to divide down optical frequencies step by step, halving the frequencies or maybe quartering it, yeah. And then eventually arriving at countable frequencies. That's one of the frequency chains that has been built, and it was a nightmare to operate, yeah. I think they had hundreds of locks, tens of lasers running, and at those times, it was very difficult to operate this even. And this is why the Nobel Prize was well deserved and given to Ted Henge and Jen Hall for the invention of the optical frequency comb. Optical frequency combs are pulsed lasers. They're femtosecond pulsed lasers where you have a superposition of modes inside the laser cavity that all constructively interfere at one given time, and that forms a pulse. Yeah? So the output of a superposition of many, many modes inside the laser cavity forms a pulse. With a repetition rate 1 over T rep, where T rep is the round trip time of the light inside the laser cavity. And then every time the laser, sort of the field hits the mirror, yeah, a pulse comes out here. So you can also think of the pulse moving, being reflected between the two mirrors, and every time it hits the output coupler, a pulse is emitted, and that's exactly the pulse repetition rate. Now, the pulse width here is given by how many modes actually contribute to the pulse. It's again the uncertainty relation delta E times delta E being larger than h bar over 2, which means that the larger delta E is, the more modes contribute, the shorter the delta T can become. And so you want a very broad spectrum to get a very short pulse time. Now, if you look at the output of this laser in frequency space, then of course it's a pulsed laser, yeah. But if you look at the spectrum, then you can recover all these individual modes that are operating or running at the same time in the cavity, and that leads to these we say comb teeth that are spaced by the repetition frequency. And if extrapolated to 0, they have an offset to 0. And that offset is given between the difference of phase and group velocity inside the laser cavity. Unfortunately, we cannot calculate this offset. And so to determine each of the frequency comb teeth frequencies, we need to determine FCEO. And the Nobel Prize was actually a technique to measure it experimentally. Because what you can do is, here again is in black, from 0 extrapolated mode structure of the comb, the resonances of the cavity of the laser, and then the actual output emission from the frequency comb here. And FCEO is exactly the difference between the two. Now, the comb equation would be that each of these modes here is given by n times, where n starts counting from 0 here, the repetition rate plus this FCEO offset frequency. And then the main point is to determine FCEO, because the repetition rate we can simply measure with the photodetector, yeah, because it's just the pulse frequency time of the laser. And what they did or came up with is that you can use the infrared part of the spectrum, frequency double it, and beat it with the blue part of the spectrum. And for this, you need an octave spanning comb. And for this, you need very short pulses. That's why short pulse femtosecond lasers and these frequency comb developments went hand in hand, and they used nonlinear fiber to broaden the comb spectrum artificially. And surprisingly, the comb structure itself remained intact during that process. And so what happens if I frequency double this, then I do not have an equation for this, but if I frequency double essentially the lower part of the spectrum here, then I double I get 2n times frep plus 2 times fCEO. And if I beat that with the upper part, then I get the same equation with twice the n, but only a single time fCEO. So the beat between those two parts of the comb, one frequency double, the other one direct, is exactly fCEO. And this is how you determine it and then can stabilize it by controlling certain laser parameters. Okay, I can use optical frequency combs. And then, of course, I've built a divider, yeah, because frep is typically a couple of 100 megahertz and fCEO is also at most a couple of 100 megahertz. These are very easily countable frequencies. And then through this equation, I can relate to optical frequencies by knowing the n, which I can find out actually. Then if I want to measure an optical frequency or compare optical frequencies, I make a so-called beat measurement of my laser frequency with the comb, and then I get the comb equation that is essentially this orange line of the comb, and then I get an additional beat frequency of my laser with that particular comb line. And then I know the optical frequency. Okay, so in essence, what you need to remember from this is that an optical frequency comb is nothing but a huge, gigantic gearbox that divides down optical frequencies into the RF regime, allows comparison between optical frequency standards and into the microwave regime. Now, if I want to compare optical frequencies, then I need to disseminate them between different points. And usually what I would like to do is use optical fibers to actually do that. I need to watch the time. Okay, couple of minutes, yeah. I'll be shorter in the next lecture then. So what you would typically do is use an optical fiber. If these are the same clocks, then I can do a direct beat measurement and get the delta F here. Yeah. Does anyone see a problem with this? The fiber can be very long, yeah, but why is that a problem? Sorry.
So you may get some loss from the clock one to
yes. So you need amplifiers.
Yeah,
yes,
exactly.
That's one problem that we need to solve. There's other problems we need to solve, even if the fibers are short and we do not need amplifiers. We have to do that in the lab actually for every piece of fiber that we have or every free space part of the clock laser.
Fiber coupling loss?
No, that's intensity noise that we can take out. Yeah. Remember, 20 seconds coherence time we want.
There is dispersion within the fiber, so that shifts
But it's a single frequency, and so it will introduce a delay that depends on the color of the fiber. But since it's only a single frequency, it's a fixed delay that we do not care about. Yeah. Have you heard of fiber microphones that are used in deep sea surveys? They use optical fibers. They put the fibers into the sea, kilometers deep, and then they can listen to what's going on down at a couple of kilometers into the ocean. Because any type of pressure, temperature, or acoustic will change the optical length of the fiber. It will introduce noise into the fiber through the Doppler effect, and that's terrible. And that will screw up our measurement essentially. And so we have to somehow get rid of that type of noise, and we do that via fiber noise cancellation systems by active cancellation. What we do is we apply a partial reflector at the end, send some of the light back. We have a reference arm here, and then a photodetector here. And that's asymmetric Michelson interferometer, where one arm, the reference arm, is very short, and this other arm can be 1,000 kilometers long, actually. And since the reference arm provides the phase information, We can then, by looking at this photodiode, learn about the noise that has accumulated on the way forth and back through this optical fiber. And we can use an acousto-optical modulator that is also passed twice on the way to clock 2 and on the way back again, and apply frequency corrections based on the beat signal that we see here, and therefore length stabilize the optical fiber interferometrically. That's what we do, even over very long distances, such as shown in this picture, where a frequency link from PTB Braunschweig over Hanover all the way to Strasbourg in France, and then all the way to Paris is shown. And PTB, Jochen Kronjäger and colleagues are operating the Strasbourg link here. It's regular telecom fibers, actually, that were in the ground anyways, but repurposed for frequency comparisons, optical frequency comparisons. They operate in the telecom regime, 1.5 micron. We have losses, 200 dB, one-way loss. That's huge, so we need amplification stages, 2 on the way, if I remember correctly. And these are, we need bidirectional amplifiers, whereas telecom providers have unidirectional amplifiers to prevent lasing in their amplifiers. And so we need to replace their amplifiers with our own amplifiers that are bidirectional, actually, to also allow for this two-way transfer. So you can go back to length stabilize the fiber. And this is the performance, again, as a function of the averaging time. This is a special form of the Allen deviation. You can see here typical clock performance. And you can see that the link does not contribute to any uncertainty in this performance. It averages down very nicely as 1 over tau, whereas clocks average down as 1 over square root of tau. Another one of the problem questions. Why is that different scaling? So they're not a limitation, actually. But nevertheless, they're difficult to install and operate and very costly because we have to pay rent for the fiber. Now, this is the fiber network or envisioned fiber network that will be set up in Europe. The dotted ones are not yet established, but in planning. All the rest has been implemented already. So that allows us to compare the clocks at PTB with clocks in Paris, NPL, INRIM in Italy, hopefully soon also in Austria and Poland and other countries. Now, that does not work intercontinentally yet because there's fixed built-in unidirectional amplifiers in all the undersea cables. And so one idea is to use optical free space links through satellites, actually, to bridge the gap to other continents. And there's a lot of problems, also part of the problem sheets that I will hand out. Okay, and I think I'll stop here and continue with the atomic reference in the next session. Thank you very much.